Hi, welcome back everybody. Today we're going to be talking about electron clouds, basically finding where an electron is in an atom. Now before we go on, I have this image here. I'm going to talk to you a little bit about it. But before I do that, I want you guys to take out your periodic tables and turn to the side that actually has the elements on it. If you look at your guys' periodic tables, kind of like down in this section, you'll see that it has a box. And it might say 1s, it could say 2s, it might say 3d, it could say 4p, depending on where you look. But down in the corner, I just want you to find those little boxes that say 3p, 4d, 5s. That's what we're going to be dealing with today. That's how we find where an electron is. Now the numbers 1, 2, 3, 4, 5, 6, 7, those represent how far the electron is away from the nucleus. 1 being very close to the nucleus. As you get bigger, 2, 3, 4, 5, 6, 7, you get farther away. Now these letters, S, D, P, and F, represent which electron cloud or an electron shape your electron is found in. Now I'm going to break down each one of these shapes, whether we're talking about the S shape, the D shape, the P shape, or even the F shape. I'm going to show you what each one of those stand for and look like. And then we're going to start doing something called orbital notation and electron configuration. And those are the last couple pages of that homework packet that you received in class. Okay, now how do we read these 1s, 2s things correctly? If you think of the periodic table as a book, when you read at the top corner and go left to right, left to right. So when I start up here with hydrogen and I read left to right, you will see that hydrogen and helium are in the 1s section. You always start with 1s. You would never start a book in the middle of the page, right? You start in the top, read left to right, and then so forth down. So after the 1s section comes the 2s section, followed by 2p. After that comes 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and so on down the line. Now this is what this image is showing. It's saying, well, start at the very beginning of the yellow brick road, and as you go down, you go 1s, you go 2s, you go 2p, 3s, 3p, 4s, 3d, 4p, 5s, so on, all the way down to 7p, and even more after that. The picture just stops after a given point. Okay? So what I want to do now is I want to start talking about what is S, what is P, D, and F. Well, S is a shape, and it is actually a ball kind of shape. 1s being a very small ball because it is the closest to the nucleus, and as you get bigger, the ball increases in size. So 2s bigger than 1, then 3 even bigger than that, 4 would be even larger, 5 even larger. So S, the number of shapes that S has is 1. Each one is represented by one single sphere. In that sphere, I can hold 2 electrons. So since there is one shape in S, and each shape holds 2, the grand total of electrons I can hold in S is 2 electrons. That is represented by the 2 sections in the S block. If you notice, there's only 2 here. There's 1 and 2, 1 and 2, 1 and 2. Now let's move on to P. P has 3 total shapes. Here's one, here's another one, and here's a third one. And when they get layered on top of each other, it kind of represents like this everlasting gobstopper from Willy Wonka kind of effect. So in P, there are 3 shapes total. Each shape can hold 2, which means that I can hold a grand total of 6 electrons within the P block area. If I go back one more time to that original slide, you will see the P block 1, 2, 3, 4, 5, 6. 6, all the way up to 6, meaning that it can hold 6 electrons. The D section is 5 shapes. Now each one of these shapes can hold 2 electrons. Since I have 5 shapes and each hold 2, you will see that the D block holds up to 10. And if you counted all of the boxes in the D block area per row, you would see that it goes 10 across. In the F shapes, there are 7 in total, each one holding 2. Gives me a grand total of 14 electrons that I can hold within that row. Now what I want to do is I want to apply this to learning how to do something called electron configuration in orbital notation. Before we jump into that, there's some rules that we have to follow. I'm going to read over the rules. You can feel free to write them down or pause the screen, or you can always just watch the videos over and over. But rule number 1 is something called the off-bow principle. It basically means an electron occupies the lowest possible energy it can first. And that is because electrons are lazy. So what I mean by this is if there is room available in the 1s box, an electron would go to the 1s box first. Once that row is completed, the next available one is 2s. Remember, reading the periodic table like a book. Start in the top left corner, read left to right. Once you're done, you drop down to the next available row, read left to right, then drop down again, left to right. So once the 1s box is filled, then we go up to the 2s. Once that's filled, we go to the 2p. 2p represented by 3 boxes because it has 3 shapes. S is represented by 1 box because they have 1 shape. You'll notice that the D blocks are represented by 5, or the D area is represented by 5 blocks for 5 shapes. F is represented by 7 for 7 shapes. The second rule that I want to talk about is something called the Pauli exclusion principle. And what that says is no 2 electrons spin the same direction. They're going to spin in opposite directions. The reason why this happens is that every electron is negative. Negative things do not want to be next to negative things, so electrons spin in opposite directions to be as far away from each other as possible. And rule number 3 says electrons enter orbitals of equal energy that are unoccupied first before they pair up. And I want you to think of sitting on a school bus, and this is where I get to show you my awesome drawing skills. So I'm going to draw a bus, and it's going to be probably the greatest bus of all time. Graphic arts has nothing on me. Oh my god, this is actually turning out very well. Oh, yeah, it's not bad. Okay, so here's the bus door. Here's my school bus. In a school bus, there's seats, right? When you get on the bus, you say you're the first person on that bus. You have so many seats to choose from. Let's say, I'm going to sit here. I'm the first kid. I'm going to go to the back of the bus because that's where all the cool kids normally sit, right? So now I'm on the back of the bus. The next person who comes on the bus, they have plenty of seats to choose from, but they could also sit with another person. Typically, if you think about how buses work, when there's available seats open, you don't really want to sit next to somebody that's already sitting in a seat because you want like your own leg room for a while. You want to be able to stretch out. You don't want to be packed next to somebody else if you don't have to. So the next person would probably pick their own seat. Let's put them in their own little seat right now. Oh man, I'm so good at drawing, everyone. All right, Now the next person comes on the bus. Now there's 3 seats available. They'll sit in their own seat. Again, not sitting with anybody else if they don't have to. Next person comes on. Okay, they're going to sit in their own seat. Last person comes on. They're going to sit in their own seat. Now, once all the available seats are taken, now when the next person comes on the bus, there is no more open seats to choose from. They're kind of forced to pair up with somebody. So we'll have the next person come on the bus. Maybe they decide to sit with this person here in this seat. Okay? And then it would just keep filling up. It would go 2 to a seat. And then the bus would be filled. Okay, so that's Hund's rule. Each electron wants their own seat before they have to pair up with a friend. Okay, so now what we're going to talk about first is orbital notation. Orbital notation is representing where an electron is, basically using arrows. So orbital notation is a visual transformation of where the electron is in an atom using arrows. How we're going to do this is we're going to represent where each electron or where each atom's electrons are. Okay? I'm going to do a couple on this page, and then I am going to then probably have to go to another one because I'm going to run out of space. Okay, let's start with hydrogen because that's element number 1. Where are hydrogen's atoms, or hydrogen's electrons? Well, hydrogen is in the 1s block. If you guys look in that little bottom corner for hydrogen, it is in the 1s block. What I'm going to do is I'm going to draw one single line, and I'm going to label it 1s. 1s because that's the area that it's in, and one line because that's the number of shapes that is in the S shape. If you remember, each S shape was represented by one sphere, one single shape. Now hydrogen, the number of electrons that it has is 1. That is why it's number 1 on the periodic table. It has 1 proton. It also has 1 electron. Now, when I go to draw hydrogen's electron, I'm going to represent that with an up arrow, meaning that its electron is spinning up. Now let's try helium. If you guys look on your periodic table, helium is in the 1s block, just like hydrogen was. So what I'm going to do is I'm going to draw one single line. I'm going to label it 1s. One line for the shape, 1s because that's the block that it's in. Now helium has 2 electrons. When I go to draw helium's arrows, I'm going to have one go up. And if you remember the rules, I told you that electrons spin oppositely. So when I go to do my second arrow, I'm going to draw it opposite of my first one. Instead of it going up, I'm going to have it go down so that it is opposite. So what this is saying is that helium has 2 electrons. Both are found in the 1s section. One spins up, the other one spins down. Now let's try lithium. Lithium is number 3 on the periodic table. But if you remember, I told you guys the off-bow principle says that I have to start first at my lowest possible energy level. You read the periodic table like a book. I have to start in the top left corner. Now lithium has 3 total electrons. That is because it's number 3 on the periodic table. Well, how do I figure out where lithium's 3 total electrons are? The very first line that I'm going to draw, I have to put 1s because that is my first possible energy level. I'm going to have 1 go up. I'm going to have 1 go down. Now, when we also talked about S, I told you that it can only hold 2 electrons, no more, no less. Once it's filled, I have to bump up an energy level. This is where we go to read the periodic table like a book. After 1s comes 2s. Another line, this time I'm going to label it 2s. I need one more arrow. I'm going to draw my arrow up. Let's try beryllium. Now, some of you might be saying, well, this is getting a little confusing. I'm a little lost here. Let me just do a few more, and I think you'll start to understand the pattern. So beryllium, number of electrons, 4. It's number 4 on the periodic table. I'm going to first do the 1s section. I'm going to go 1 up, 1 down. Then I'm going to go over, I'm going to do 2s. I'm going to go up, then down. 4 electrons, 4 arrows, up, and down. Next is boron. Boron has 5 total electrons. 5 total electrons, each represented by an arrow. I'm going to start in the 1s block, up, down. Then I go to the 2s, up, down. I can't fit any more in the 2s. That means I have to bump up another energy level. After the 2s comes 2p. But if you remember, I told you that p is represented by 3 shapes. Well, s was represented by 1 shape. We drew 1 line. P is represented by 3 shapes, which means I have to draw 3 lines. And I'll label that 2P. I'm going to pick one of these available seats. I'm going to put my arrow in one of them. Again, think about the bus example. Just pick a seat, pop an arrow in. After boron, carbon. Carbon has 6 total. We'll start at 1s. I'll go up, down. Now I'm going to go over to 2s. Up, down. Now I'm going to go to 2p. Again, I'm going to represent it by 3 lines, just like we did for boron. I'm going to go up. Now I need one more arrow in carbon. Am I going to pair him with a partner when I have available seats open? I think not. I have these empty seats, just like the bus example. What I'm going to have it do is get its own seat. I'm going to draw it going up. After carbon comes nitrogen. Nitrogen represented by 7, so 7 total arrows for 7 electrons. 1s, up, down. 2s, up, down. I do the 2p, 3 lines for 3 shapes. So I go up, up, and I still have 1 available seat over here, so my 3rd electron will get its own seat. Then comes oxygen, 1s, up, down. 2s, up, down. Now I'm in the 2p. Each electron first getting its own seat. Now I'm at 7. I need 1 more. I'm going to pick one of these seats and start to pair them up. But when I pair them up, they have to spin oppositely, just like they did here. So this one, I'll go down. Fluorine next. Up, down. Up and down. Now I'm going to the 2p. It's going to go up, 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 each getting its own seat. and I'll have a down, and I'm one arrow short, so I'm going to put another arrow again in a seat, and I'm going to make it spin oppositely. The last one in the row, neon, 1S, up, down, 2S, up, down, 2P, it'll go up, up, and up, and then down, down, and I need one more, down. Okay? So basically, these arrows are representing where the electrons are. You first have to start at the 1s level. You give it 2. Once you have that, you then move to 2s. You would give that 2. Then you go on to the 2p. Since 2p is represented by 3 different shapes, you have 3 lines. Each one can hold a grand total of 2 electrons. Let's just try 1 or 2 more. Let's do sodium, because that's number 11 on the periodic table. I would start at 1s. I'd go up, and I'd go down. After 1s comes the 2s section. I go up, and I go down. After 2s comes 2p. Up, down, up, down, up, and down. And then 2p is now filled. There's no more room in 2p. I can't add any more arrows. I have to bump up another energy level. After 2p, I told you guys, comes 3s. I'm one arrow short. I will have it go up. Okay? So that is orbital notation, representing where an electron is using arrows. Give that paper a try with orbital notation, and I'll be back for one more video showing you guys how to do electron configuration.